In the final video of today, let me solve two example problems. First example problem is related to the first topic we covered, which is asymmetric loading problem. And second example is about stress concentration. So let's solve the first problem first. So because I haven't given you any real problems with real specific numbers, I prepared two example problem. So in the first problem, we have the beam under bending. However, this bending is not applied to either of this principal axis, and it's applied at 30 degree from the horizontal axis. Okay, and the dimension of this rectangular cross section is 40 millimeter here and 90 millimeter in height. So the problem asks what is the maximum stress, and also what is the angle between neutral plane and horizontal plane. Okay, because neutral plane is not, parallel to the moment in this kind of asymmetric loading. We have to calculate and predict where is the location and orientation of a neutral plane. So let's try to attack the first problem, maximum stress. So to do so, as I told you, we have to decompose M into two parts, mg part and my part. Okay, so regarding mg part, we have to do cosine 30 degree calculation, and regarding my, we have to do sine 30 degree multiplication. And after multiplying this factor, mg turns out to be 155.9 and my turns out to be 90 Newton meter. Okay, and here, even though my is much smaller than mg, what you can see here is, if you consider bending of the beam in this direction, we see like a lot of mass in top and bottom, right? Like the same area distributed along like a y-axis, so that you can expect that the area moment will be quite high. However, when you try to bend with respect to this my moment, then the materials are rather distributed near the centroid, right? In that direction, we don't have like a less distribution, so that you can expect that area moment with respect to these kind of bending will be relatively small. Okay, so let's try to get the number. So regarding the mg deformation, if we obtain ig and we do 1/12 0.04 meter, because it's 40 millimeter, and the height is 0.09 meter, and if you do this calculation, this is the value of ig you're gonna get regarding this kind of bending. However, when you consider my component and try to obtain iy, and then instead of b, you have to multiply h here, and you have to put b cube here and plug in 0.09 and 0.04, you can see that the iy is much smaller than ig. Okay, so even though we are considering exactly same area here, this is where you can see the effect of the orientation. Okay, so for exactly same shape and exactly same area, depending on the orientation, you can have significantly different area moment of inertia. Okay, so for each problem 1 and problem 2, you can obtain sigma x distribution from minus mg y over ig, and from second problem you have mig divided by iy, and please be careful about the sign convention, as I told you in the video regarding the first topic. Okay, so if you plug in numbers, and let's try to obtain the maximum stress. So maximum tensile stress from the first problem will occur like this bottom point, right, when you have minus 0.045, which is the distance from the center to bottom. And if you plug this number, and if you plug the number for mg, if you plug the number for ig, this is what you're gonna get. And if you obtain the maximum stress from the second problem, you plug in my, you plug in the location where the stress becomes maximum, and the location turns out to be here. Okay, z equal 0.02 meter or 20 millimeter. Okay, and you plug in iy value, and you can see that even though the moment is much smaller in y direction due to much smaller iy, you can see that stress becomes even higher. Okay, it bends further you know with respect to y-axis. Okay, anyway, by combining these two answers, you find that the maximum stress in turns out to be 6.637 megapascal, and that location will be here because from first problem you have maximum at y equal minus 0.045, and for the second problem you have maximum here. So by considering both problem, this is the point where you're gonna have this large tensile stress. Okay, and this will be the answer for the first problem. And for the second problem, what you do is we simply apply our equation, because the geometry is exactly same as our sample problem, except that we considered like a T shape in lecture. Here we are considering a rectangle, but even for this rectangle you have very different iz and iy ratio, so we can simply apply that equation. And the angle between moment and horizontal line was 30 degree. You can obtain tan phi very easily. So tan phi turns out to be 2.923, and if we obtain phi out of this, it turns out to be 71.1 degree. Okay, so if I visualize the orientation of a neutral axis, it has 71.1 degree from the horizontal line, whereas the moment vector was 30 degree from the horizontal line. Okay, so you can see that moment vector and neutral axis is not parallel to each other for this asymmetric loading problem. Now let's try to solve a second example problem. In the second example problem, we have external moment m as 180 Newton meter, and the problem asks and give a constraint that the maximum stress out of this bending should be smaller than 150 megapascal. Possibly, that will be the allowable stress of the material. Then the problem asks us what will be the smallest width of the groove that we can make. Okay, so if we look at the geometry from the problem, we have the large distance 60 millimeter. We have like a 10 millimeter and 10 millimeter depth to this sort of crack. So you can see that this D is 40 millimeter. Okay, and this is front view, and the side view. The side view, thickness is 9 millimeter, and this is 40 millimeter, and the C distance to the top and the centroid, this is C, turns out to be 20 millimeter. Okay, so given this geometrical information and given this moment m, we can try to obtain the maximum stress using the stress concentration consideration. So these are geometry, and we can obtain I in this section. We have to obtain I in this section, this small width section, and I turns out to be 48 times 10 to the negative 9th power, okay, in SI unit. Okay, so and if you plug this I into the calculation of sigma x, and at y equals c at this top point, without considering the stress concentration factor, if you do mc over I, you multiply 180 Newton meter, and c is 20 millimeter, which is 0.02 meter, and if you plug this number, you're gonna get 75 megapascal. Okay, however, 75 megapascal is not a correct answer, because there should be stress concentration effect, and if we consider the constraint of the problem, the maximum stress must be smaller or equal to be 150 megapascal, and by considering this stress without stress concentration, what we can infer is K must be 2 or smaller. Okay, so we have to obtain K equal 2 location out of the stress concentration diagram. So first, let's take a consideration between the ratio between d and small d, and d and small d ratio is 1.5. Okay, and d is given as 40 millimeter. So we have to obtain for ratio for the value of r when k becomes 2. So when d over d is 1.5, when d over d is 1.5, yeah, this is the line, right? So let me use different color. This is, yeah, when d over d is 1.5 case. If we consider k equals to be 2 point, okay, yeah, this is it. Yeah, so what you can see here is small r and small d is around 0.13. Okay, when you consider 0.13 ratio and plug in d equals to be 40 millimeter, yeah, then r must be 5.2 millimeter. Okay, and if you multiply 2 to obtain the width of the group, yeah, it will be 10.4 millimeter. That will be the answer for the problem regarding stress concentration. Okay, so regarding the application of stress concentration, yeah, I'm sure that you have already solved the stress concentration problem in normal loading and torsional loading. You must be quite familiar with this. Okay, so for bending it's the same. If you have correct definition about stress concentration, you can figure it out by yourself and you can solve the stress concentration problem without any difficulty. Okay, so with this, by providing 2 example problem solutions, let me finish my lectures on bending here. In the next lecture, yeah, we'll consider some loading considering our final reaction, which is shear force V. Okay, so until now we covered N and T and M, 3 reactions. Out of 4 reactions, we have 1 more, and that will be the topic of our next lecture.